In this video, I'll talk about the three types of solids: molecular solids, ionic solids, and atomic solids. Let's first look at molecular solids. There are a few examples here. Water in the solid phase, CO2 in the solid phase, solid oxygen, and long carbon chain fatty acids. For example, lauric fatty acids. There are two different types of interactions that hold these molecules together in the solid phase. One is dispersion. For example, between two neighboring oxygen molecules, there is dispersion. Or dipole-dipole interaction. For example, between two water molecules, there is hydrogen bonding, and hydrogen bonding is the strongest type of dipole-dipole interaction. Between two fatty acids, mostly it's dispersion, and if you have a longer carbon chain, there will be more dispersion. The melting point between molecules in the molecular solids can be from negative 200 degrees Celsius to positive 100 degrees Celsius. Ionic compounds made of positive and negative ions. So over here we have sodium plus, chlorine minus, potassium plus, bromine minus, calcium plus. This is carbonate, negative ion, or anion. The attraction between the positive metallic cation and this negative anion is so-called electrostatic interaction or ion-ion interaction. This electrostatic attraction is very strong. That's why the melting point of ionic compounds is typically 500 to 3000 degrees Celsius, very high melting point. It's very hard to melt, for example, even sodium chloride. Well, you can try this in your kitchen, but you're not going to succeed. Finally, atomic. This is the third type of solids. And there are three subtypes: non-bonding, network covalent, and metallic. So first, non-bonding atomic. One example, solid argon or solid xenon. Those are noble gas atoms. What's holding those noble gas atoms together? It's dispersion. Again, even for a argon atom, it's possible to have a non-zero dipole because the electrons in the argon atom move around. At a certain moment, it's possible the uneven distribution of electrons may create an instantaneous dipole, and then that dipole may induce a non-zero dipole in a neighboring argon atom. And these two instantaneous dipole and induced dipole may have attraction. So that's holding the argon atoms together in the solid phase. But this dispersion is really, really small. Therefore, the melting point of solid argon or solid xenon is very low, roughly negative 200 degrees Celsius. Second subtype of atomic solid, network covalent. For example, diamond, you have carbon-carbon covalent bonds. Graphite, similarly, you have carbon-carbon covalent bonds, but in graphite you will see actually double bonds between carbon and carbon atoms. And also you will see there are layers of graphene sheets. So between the two neighboring graphene sheets, that's mostly dispersion. So there are like covalent bond, but there's also dispersion in this case between graphene sheets. Quartz silicon dioxide. Later I will show you the structure of this silicon dioxide crystal. So mostly those in those network covalent atomic solid, atoms are connected by strong covalent bonds. Because covalent bonds are strong, the melting point is usually 3000 or 4000 degrees Celsius. The third subtype of atomic solid is metallic. So you just need to know those metals consist of just metallic atoms. These atoms are held together via metallic bond. And metallic bonds are like metallic nuclei being immersed in a sea of electrons. This is because in metal solid, the valence electrons can move freely. So you just imagine all those valence electrons form an ocean of negative charges, and then the nucleus, the metallic nucleus with core electrons, overall it's still positively charged. They look like islands inside the ocean of electrons. So that's metallic bonds. The valence electrons attract the metallic nuclei. That's what is holding those atoms together. So this metallic bond is weaker than covalent bond. Therefore, the melting point of metal is lower than the melting point of this network covalent atomic solids. It's usually between 0 to 1000 degrees Celsius. So later, if you take physical chemistry, I will show you a video of putting sodium and potassium together, mix them, and then they melt at negative 6 degrees Celsius. Alright, let me show you a few structures. This is ice. So each red sphere is oxygen. Those yellow spheres are hydrogen atoms. Between two neighboring water molecules, there's hydrogen bonding or hydrogen bond. So you can see this stick is a hydrogen bond. This stick is a hydrogen bond. Now let's look at this dry ice. So each molecule is a CO2 molecule, and you can see between these two neighboring CO2, there is so-called dispersion or London force that's holding these two CO2 molecules together, because the CO2 molecule does not have a non-zero dipole moment. So they are held together by this dispersion force or London force. Over here, this is KBr, potassium bromide, or you can see it can be also chloride. So the larger spheres are chlorine minus or bromine minus. The smaller ones are potassium plus. And we have this H lens A here. This is solid argon. You see a lot of argon atoms. And this unit cell is a face-centered cubic unit cell. This one is gold. You see a lot of gold atoms. And between two gold atoms, we call that bond metallic bond. And over here, this is quartz, silicon dioxide. And you can see between the atoms, there's covalent bonds. And covalent bonds are typically strong bonds. That's why quartz has a very high melting point. Alright, now I'm gonna ask you to work on this practice problem. Classify each crystalline solid as molecular, ionic, or atomic. 1, 2, 3, 4, 5. There are 5 questions. Chromium, nitrogen, aluminum oxide, xenon, diamond. So you may pause here and work on this yourself before I show you the answer. So now it's the answer, chromium. It's a metal, so it's metallic atomic solid. Nitrogen. Nitrogen is a molecule, so it's possible to solidify nitrogen gas. It's a molecular solid. The interaction between two neighboring nitrogen molecules is dispersion or London force. Alright, over here, aluminum oxide, it's ionic. You have aluminum 3 plus and oxygen 2 minus. The positive aluminum 3 plus and the negative oxygen 2 minus attract each other. Xenon, non-bonding, atomic. Again, xenon atoms are held together by dispersion. Diamond, this is network covalent because there is covalent bond between two neighboring carbon atoms.